Consequently, if we were to find some other vector which is less than 400 or 350 bits away from x, then the chance of that happening purely at random is very small. So if this vectors represent objects, it's highly likely that these two vectors represent the same object. In many ways, what we've done here is very reminiscent of locality-sensitive hashing. However, associative memories differ from LSH or even indexing in that they don't really store the objects. So what they do instead is they choose a set of random vectors, a large number, m, could be 1,000,000, but certainly not anywhere nearly as large as the space itself. And instances that are seen by this memory are associated with these random vectors in some additive way. And we won't go into that in great detail, but the essence is that if instances or objects differ in even 400 bits, they are easily identified because of the properties of the high-dimensional spaces. Further, because of the way SDMs store instances, not as individual objects, but as combinations, the SDM is able to recall when presented with a query object by constructing an object from the history of all the objects it might have seen in the past. So instead of a set of search results, an associative memory returns an object, which is the memory's best guess of what the input object is. The best guess that it returns might never have actually been seen by it before, which is the interesting part. If you think about human memory, when we recall something, we don't recall it in great detail. We are constructing the object that we're recalling or the experience based on many impressions that we might have received in the past. Why are associative memories at all important? It turns out that apart from the deep relationships between them and dimensionality reduction methods like LSH, techniques based on sparse representations have become extremely popular in the recent few years. We'll return to some of these ideas, at least intuitively, towards the end of the course when we discuss the predict element in our cycle. Let's conclude now by asking whether looking is the same as searching. When we look around a room, for example, and recognize objects and people doing activities, we're not really searching for anything. Or when we're browsing a bookshelf, or flipping the pages of a book, or even looking at some data, like some time series, or a histogram, or charts, to see if there might be any hidden patterns in the data. In the first case, while seeing, we are visualizing a scene. Computationally, this involves techniques such as clustering and classification. In the second and third examples, we're trying to get a feel for a document, a collection of documents, or some data, which requires techniques such as automatically summarizing documents, discovering the topics in documents, and discovering interesting correlations in data without direct intervention. Each of these are deep research areas of current interest, and we'll get into them as we go beyond looking to listening, learning, connecting, and predicting.